In this lecture, let us discuss about recurrent neural networks, which are designed to process sequential data like time series, natural language, speech, and video frames. Unlike traditional feed-forward networks, RNNs have an internal memory that allows them to retain information from previous time steps. So at every time step t, RNN processes an input, updates its hidden state, and generates an output. So if you take this input at time step t minus 1, okay, so RNN process this input, then it will update the hidden state, which is at minus 1, and generates output yt minus 1 hat. The key difference from feed-forward networks is that recurrent connection that propagates information across various time steps. So in this picture, you can just see input, hidden state, and then the output. But the internal representation for this hidden state will be combination of RNN cell plus hidden state. So I'll show you that while explaining the example. So how the things will be processed means, see, if you take this input at time step t minus 1, so this input will be passed to the RNN cell. Say RNN cell is placed here along with the initial hidden state. So there will be two parts here. In this diagram, only the hidden state was represented. And this initial hidden state will be usually zeros. Okay, so this will be usually zeros as it is not having any previous data, as this is the initial hidden state. And the RNN computes the new hidden state at minus 1. So based on the previous hidden state as well as the current input, okay, RNN computes the new hidden state at minus 1. Then RNN uses this at minus 1 hidden state in order to produce the output yt minus 1 hat. Similarly, at time step t, again, one more word is passed into the same RNN cell along with the previous hidden state. RNN computes new hidden state at and uses this at in order to produce yt hat. Okay, so this process repeats for the third input at time step t plus 1. It takes the RNN computes new hidden state. So here the input, this input will be passed to the RNN cell along with the previous hidden state, that is at minus 1, and this RNN will compute new hidden state at plus 1 and uses this at plus 1 in order to compute yt plus 1 hat. So this process will be repeated for n number of words present in a sentence. Then what is the difference between this RNN cell and hidden state? Why this RNN cell is not represented separately here? So here both of them are different. See, RNN cell means it's a computational unit that process one word at a time. So it will take the input word vector as well as the previous hidden state. So this is a word vector, input word vector as well as previous hidden state in order to compute the next hidden state. Okay, that is represented as RNN. So that will be represented as RNN here. Whereas the memory of RNN, so which is storing contextual information from the previous word, is nothing but the hidden state. So this hidden state is updated at every step and it is represented as at minus 1, at plus 1 and so on. And at every time step, RNN performs various computations by using a formula. So it will perform the hidden state update as well as output generation. So we'll see all those formulas and the notations present in this diagram in detail. These are the key components of RNN architecture. First one is input, represented with xt minus 1, xt plus 1. So they represent the input data at different time steps. So these are the time steps t minus 1, t plus 1. At each time step, RNN takes an input which could be a word in a sentence, or if it is an image data, then it can be pixel value in sequence of images, or it can be any other time dependent data. And if you take this example, say the sentence is, I love to read, then these are the words that are given to every input state at every time step. So, say, suppose the input word assigned to this RNN cell at time step t minus 1 is I. At time step t, input word is love. At time step t plus 1, input word is 2. So, here we are providing I love 2. Again, directly we don't give these words to the RNN cell. So we'll provide only the vector embeddings of these words or numerical representation of these words to the RNN cell. Then coming to the hidden state, so it can be represented with either H or AT minus 1, AT plus 1. So this is actually represented with green rectangles in the diagram. So you can see that hidden states are represented with green rectangles. So this mainly stores information about the past inputs and also helps influence future predictions. Okay. So this hidden state maintains memory of previous time steps, and this hidden state is updated at each time step using the input as well as previous hidden state. So we'll see that notation also how it will be done. And the activation function is typically a nonlinear function like tan h or ReLU. The hidden state helps the RNN remember past information. So, what this hidden state does, at every time step t, denoted with either AT or HT, stores information from both the current input as well as previous hidden state, that is AT minus 1. And this is a mathematical formula. Here f is a activation function. Usually it can be either tan h or ReLU. Then coming to all these components. So this AT is nothing but hidden state at time t, which represents memory of network at time step t and is computed using previous hidden state AT minus 1. So this AT minus 1 is used to predict this AT as well as current input xt. So both of them are used. Then coming to AT minus 1, this part. So that is previous hidden state. Okay, AT is nothing but current hidden state and AT minus 1 is previous hidden state. This AT minus 1 stores information from the previous time step and helps capture sequential dependencies in the data. Then coming to XT, current input at times t, right? So in applications like NLP, it can be word embedding. Whereas if you take time series forecasting, it can be a numerical value. Then coming to this W. So this can be represented with WH also, which is hidden to hidden weight matrix. So this weight matrix determines how much influence the previous hidden state AT minus 1 has on the current hidden state AT. Then we have U. Okay. This is nothing but input to hidden weight matrix. So this previous one W is hidden to hidden weight matrix, whereas U is input to hidden weight matrix. So this matrix defines how the input affects the hidden state. So just like WH, this is also learned during training only. Then we have terms like B, bias. Bias term is added to improve the flexibility of the model and it helps in shifting the activation function as needed. Then F is a activation function. So just now we discussed that, which introduces non-linearity into the model. And here the tan h ensures that the hidden state value remains between -1 and 1, preventing uncontrolled growth. Whereas if you use ReLU as activation function, it helps mitigate the vanishing gradient problem, but it can lead to dead neurons also. So this equation, it allows the RNN to remember past information while incorporating new inputs over time. Then there are components in the hidden state also. So if you take previous hidden state, AT minus 1, okay, so this hidden state acts as a memory, helping the network retain information from the past input. And the previous hidden state, AT minus 1, captures past dependencies and is used to compute the current hidden state, AT. So mainly it stores memory of the previous time steps. So say suppose if you are reading a sentence like this, I love to read. At time step t minus 1, RNN read this two words, I love. Then at time step t, so based on the previous time steps, it should read next word as to, right? So in that way, this previous hidden state captures past dependencies and is used to compute the current hidden state. So why this AT minus 1 is important? Because it captures temporal dependencies. Okay, as the hidden state stores information about the earlier time steps, it helps the model learn sequences. So what will be the next word in the sentence? So it can predict that. And also it enables the context understanding also. Say if you take words, if you take a sentence like the cat sat on the mat because it was comfortable. So what is the sentence? The cat sat on the mat because it was comfortable. So then what this it refers to? So how the machine will identify that? So in order to predict that this it refers to mat, hidden state is useful. Okay, because this hidden state remembers that it refers to mat, it helps this RNN to identify that it is nothing but mat in the sentence. Next one is input to hidden weight matrix. This matrix transforms input into a format compatible with the hidden state. So that means, see, whenever the input is given, that should be converted into a form such that it will be comfortable for the hidden state to handle that. And here, it mainly transforms the input feature vector into hidden state space and determines how much of the current input influences the hidden state. So if this U is properly trained, then it ensures that network effectively capture input dependencies. Say for example, if xt represents a word love, then this hidden or input to hidden weight matrix, it helps to represent this love in a numerical format. Okay, so it will encode its meaning. So uxt will encode its meaning into a numerical format. Then coming to hidden weight matrix. So this is again responsible for propagating information through time, and it helps the network retain memory of previous time steps by influencing the current hidden state. And also it controls how much of the previous hidden state should be remembered. This is most important. So only as it is having limited amount of memory storage, it should not remember all the unnecessary things or the things which happened in the past long back ago. So it can't remember that. So how much part of the previous hidden state should be remembered will be controlled by the hidden to hidden weight matrix. And it also determines how this past knowledge influences the current state. Say for example, if this AT minus 1 hidden state stores words I love, then this WAT minus 1, it ensures that this love is remembered when processing 2. Okay, when processing the next word, it makes sure that this love is remembered. Then we have weight matrices. So represented with U, W, and V. So this U is nothing but input to hidden weight matrix, right? It maps the current input to the hidden state. And the shape of this will be H comma D, where H represents the hidden units and D represents input features. It determines how much the current input influences the hidden state. Then coming to W, hidden to hidden weight matrix, it governs the transitions from previous hidden state HT minus 1 or AT minus 1 to current hidden state AT. Okay, so it mainly connects AT minus 1 to AT. And shape of this matrix is H comma H. So this is hidden to hidden, right? This is square matrix. And it retains memory and propagates temporal dependencies across the time steps. Then the last one is V, which is hidden to output weight matrix. So remember this. This is input to hidden, whereas this is hidden to hidden, and this is hidden to output. So that is most important. So you need to know the difference. And the shape of this matrix is O comma H. O is the output size and H is hidden units. So this V, it converts the hidden representation into meaningful output. Then coming to the outputs represented with yt hat, yt minus 1 hat, yt plus 1 hat, and it is represented as blue circles in the diagram. You can see these are the outputs. Okay. So this output layer, it mainly generates prediction based on the current hidden state, and the type of output that will be generated from this layer depends on the type of task, whether it is a classification, regression, or translation. So based on that, output will be generated. And in this, yt is nothing but the predicted output at time step t, whereas yt minus 1 hat, it is a predicted output at previous time step. Yt plus 1 hat is a predicted output at the next time step, right? And there is a notation here, yt hat equal to g into vht. Okay. Say this in this, yt hat represents predicted output at time step t, whereas v is a weight matrix connecting hidden state to output. Just now we saw that. And G is the activation function. So based on the type of task, the suitable activation function will be used. Say if the task is classification, then softmax activation function will be considered. And this V value, say if this V value is too small, then the outputs may be weak. Okay, they are considered to have low confidence. If this V is too large, predictions may be unstable. So proper training ensures this V correctly maps features from the hidden state to the output.